Okay, first of all, please subscribe my channel and please watch my videos online. In this lecture, I want to prove a very important theorem about the Hermit interpolating polynomial. So let me write the title. A theorem about Hermit interpolation. We saw before that a polynomial like Pm of x, okay, where m is k plus 1 times n plus 1 minus 1, okay, is Hermit interpolating polynomial if the kth derivative of p at a nodal point xi be equal to the kth derivative of f at nodal point xi for k equal to 0, 1, 2 mi minus 1 and I equal to 0, 1, 2, n. In fact, Pm of x is a Hermit interpolating polynomial if the derivative of p and the derivative of f at a nodal point like xi up to order k be equal. In fact, p interpolate f and the first derivative, second derivative, up to kth derivative of f. Okay, now in the continuation we let mi be equal to 1 and I be equal to 1 to n. So in this case, okay, the Hermit interpolating polynomial is a polynomial like Pm or p in fact, such that p of xi be equal to f of xi. In fact, this is the zeroth order derivative of p and f, and p prime of xi be equal to f prime of xi for I equal to 0, 1, 2, n. Okay, in this case, by this formula, okay, we will have k equal to 1, okay, and n be equal to small n. So m will be m will be 2 times n plus 1 minus 1, and this will be 2n plus 1. So p 2n plus 1 of x is Hermit interpolating polynomial and we want to give a formula to find this p2n plus 1 for Hermit interpolating polynomial. Let me state and prove a theorem. This theorem is in fact the most important theorem for Hermit interpolation section. Okay, now let me write the theorem. Let f be in C1 over interval a and b. It means f and f prime on a and b are continuous. Okay? And suppose that x0, x1 to xn be a set of distinct points in interval a and b. Then this is in fact a claim of the theorem. Then there exists a unique polynomial, of degree at most 2n plus 1 such that interpolate f of x and f prime of x at x0 to xn, and this polynomial is to form, we show it by h2n plus 1 of x equal to sum j equal to 0 to n f of xj times h n and j at x plus sum j equal to 0 to n f prime of xj times h hat n and j at x, where h n and j of x defined by 1 minus 2 times x minus xj times L prime n and j squared at xj times ln and j square of x and h hat n and j of x is equal to x minus xj times ln and j squared and x. Okay, also we know that ln and j of x is the Lagrange polynomial to form pi I equal to 0 to n, I not equal to j, x minus xi over xj minus xi. Okay, this is the first part of theorem. Moreover, the error term of h2n plus 1 is f of x minus h2n plus 1 of x is equal to the n2n plus 2 derivative of c over 2n plus 2 factorial times x minus xi squared. Okay? Where there exists xc of x in open interval a and b, and also we have to note that should the 2n plus 2 derivative of f exist. Okay, this is a very long, in fact, theorem. The title of the theorem is very long, and now we want to start to prove the theorem. So let me start the proof. First of all, we have to show that h2n plus 1 interpolate f of x and f prime of x at every xi for I equal to 0 to n. Okay, so consider h2n plus 1 xi. So we should show that h2n plus 1 at xi is equal to f of xi for I equal to 0 to n. We have to prove this equality. Let me put a question mark here. We have to prove this equality. Okay, consider h2n plus 1 at xi, okay, and use the formula that I have written here. Okay, j equal to 0 to n, f of xj, hnj, xi. In fact, here xi should appear, and also here h hat nj xi should appear here. Okay, so let me put and start to compute. J equal to 0 to n, f of xj, h, n and j at xi plus sum j equal to 0 to n, f prime at xj, h hat n j xi. Okay, also we know that L, N and J at xi will be 1 for j equal to I and 0 for j not equal to I. Okay, so if you look at here, if you look at here, and if you look at the definition of HNI, and let me look at something. Now, let me have a look at H, N, and J at X. We wrote in the first of this lecture, this is equal to 1 minus 2 times x minus x j, L prime n and j times xj times L n and j xi. squared. Okay, so this gives that h, n, and j at xi, okay, will be equal at xi, will be equal here. If if j be equal to I, okay, let me clear it. Now, if you put this h and j here in the sum for j equal to 0 to n, okay, we know that if j be equal to I, this value will be hn and I xi, and in other cases hn and n and j at every other point of I, it will be 0 because of this one. Okay, and also the same thing for h hat is true. H hat n and j at x is equal to x minus xj times lnj squared at x. Okay, so by these two equality we can get h2n plus 1 at x is equal, just for j equal to I, the good thing happened. In fact, in other cases that j is not equal to I, all terms will be 0, and just we should have f of xi times h, n, and I at x plus f prime at xi times h hat n and j at xi. Okay, so now we have to compute this term. We have to compute this term. Okay, and this term. Let me compute these two terms. Consider hni, consider hni at xi. Okay, here put instead of j equal to I, so I get 1 minus 2 times xi minus xj times L prime n and I. In fact here it should be, oh no. Yeah, here it should be I also. Yeah, I, right? Let me fix it. I times L prime n I, look at here, n I at x, I times L squared n I x I. Okay, we know that this term will be 1 by here. Okay, and also this will be 0. Okay, so this term totally will be 0, and from the first part remain 1, and let me have a look. Yeah, 1 and here 1, so totally it will be 1. So this term is 1. Okay, keep it. Now let me compute h hat n and I at xi. Put here, it will be xi minus xi times ln I xi. Okay, if you have a look at it, it will be 0, so this term will be 0, and the other part, this one, will be 0. Okay, so it will be equal to f of xi times 1 plus 0, so it will be f of xi, and it works for in fact h2n plus 1 at xi in fact interpolate f. Let me of course clear this one, and I can write something here. So h2n plus 1 at xi will be equal to f of xi for I equal to 0 to n, and it means h2n plus 1 of x interpolate f of x. Now we have to do something same for h2n plus 1. Now we have to show that h prime 2n plus 1 at xi is equal to f prime at xi. Okay, now I have to show this equality. Okay, let me start to show this item. Consider h prime 2n plus 1 at x. Okay, it's sum j equal to 0 to n. We know that f of xj, it should be xj, times h prime n and j at x plus sum j equal to 0 to n, f prime of x j, h hat prime n and j at x. Okay, now I have to in fact compute h prime n and j and h hat prime n and j. Okay, so let me do the computation. We had before h n and j of x is equal to 1 minus 2 times x minus x j times L prime n and j at x j times L n and j squared at x. Okay, am I right? Yes, this is true. Now I have to compute in fact h prime n and j. Take derivative from both sides. Here we will get n and j x prime is equal to the first part derivative, which means 1 minus 2 times x minus xj times L prime n and j xj derivative, the first part, times L squared n and j x plus the second part, the second part by times the first part will be 2 L prime n and j at x, L n and j at x times 1 minus 2 times x minus xj times L prime n and j at x j. Okay, now if you consider h prime n and j times n and j at xi, so if j not be equal to I, then h prime n and j at xi will be. Here if I not b equal to j, so this term will be 0, so this term totally will be 0, and also this term will be 0, so totally is 0, so h prime n and j at xi will be 0. But for j equal to I, we have, okay, put in this equality x equal to xi, and note that j should be I. So I get n h prime n and I times xi, okay, is equal to here 1 minus xi minus xi, it will be xi minus xi times L prime ni xi prime times L squared ni xi plus, and here 2L prime ni xi L ni xi times 1 minus 2 times xi minus xi L prime ni at xi. Okay? Now, I think I had some mistake here, and before I put x equal to xi, I should compute the derivative of h at x. So let me clean this computation and repeat it. Okay, so first let me compute this derivative. So h prime n and I at x should be equal. Okay, here the derivative of 1 is 0, and here minus 2 times L prime, so I will get minus 2 times L prime n and I, it should be I at x, I, correct? Yes. Then minus 2x minus x I times L double prime n and I at x I. This term computed. So this is inside times the second part L squared n and I at x, okay, plus let me have a look again. Yeah, it's correct. So I have computed this derivative, and I have to put the second part, in fact, plus 2L prime n and I at x, okay, L n and I at x times 1 minus 2 times x minus xi L n and j prime at x, correct. Now put instead of x xi, okay, so if I put instead of x xi here, it will be xi here and also xi here and also xi here, xi here, xi here, and finally xi here. Okay, now Look at here. If you put instead of x equal to xi, the first part here we keep it, okay? And let me consider something. This should be 1, right? This should be 1, and this will be 0. So from the first part it remains just, so from the first part it remains just minus 2l prime n and I at xi, correct? Just this one. And here this one, this one is 1, and also this is 0, 1, this is 1, and here it remains just plus 2 L prime n and I at xi. Look, minus 2L prime plus 2L prime, and it is equal to 0. It's equal to 0. So we get h prime n and I at xi is equal to 0. And also we had for I equal, for every I equal, not equal to j, for every j not equal to I, it was 0. So this is equal to 0, so we can get, so h prime n and j at xi equal to 0 for j equal to, for I equal to 0, 1, 2, n. Keep it. I want to use it, in fact, here. So this will be 0, and I can use it a little later. Now we have to compute h hat prime n and j. Now we compute h hat prime n and j at x. Okay, let me compute it first and then put instead of x equal to xi. So h hat prime n and j at x is equal to, okay, let me show you something here again. We had here the first derivative times the other one and the second one times the first one. It's very easy to compute. Let me compute the derivative L squared n and j times x plus 2 times x minus xj times L and j times x times L prime n and j times x. Okay, now if j be equal to, is not be equal to I, if j not equal to I, then h hat prime n and j at x j at xi, sorry, at x I. Look at here, if you put xi here, okay, this term is 0 and this term is 0, so totally it's equal to 0. Okay, and if we let j be equal to I, we can get h hat n and j times x, so put n and I times of xi, so it will be L squared n and j, L and I, sorry, n and I xi plus 2 xi minus xi L and I x times L prime n and I x I. Correct? This is true. Now, consider here, this term will be 0 and it remains just this one, and this is equal to 1. So it's equal to 1. Okay? So, if you write h2n plus 1 at xi is equal to f of xi h n I xi plus h prime xi, this one is h prime also, plus f prime of xi times h hat n and I at xi. This one was 0 and this one was 1. So totally it will be f prime of xi, and it means that, so h2n plus 1 of x interpolate f of x and f prime of x at x0 to xn. Okay, this is the proof of the existence. In the next lecture, I will prove the uniqueness and the error term for the Hermit interpolating polynomial. So please follow me and subscribe my channel and wait for the next lecture. And please do not download the video and watch online. Thank you and wait for the next lecture.